All right, we are almost done here. Can you believe it? So last time we talked about in 6.7, or sorry, 6.6, how to solve exponential equations. And now in 6.7, we're going to be talking about how to solve logarithmic equations. Okay, so ones that start with a log in them right off. Okay, so let me write that down here. It's not recognizing my pen. Hold on a second. Oh, because I'm using the wrong one. All right, so 6.7. All right, so hopefully it's been clear to you, because this whole chapter we've been talking about exponentials, we've been talking about logs, and how logarithms undo exponentials, right? So they're an operation that is like, like add, subtract, multiply, divide, square root, square, all of those things are operations that you're doing to either, numbers or variables. And so when you see that word log, remember those aren't the log, it's not a variable, right? I mean, you should think of it as like one of those little symbols that, means to do something, right? This operation sort of thing. So, so let's talk a little bit about how we're going to go about solving these log equations, right? So let's start off with log base 2 of 64 equals x. Right? So we've seen some like this earlier on, and we kind of, even though we weren't really solving for it, we were changing from one form to another. What really happened was that, we kind of were solving for it. So these should look a little bit familiar there. So first thing that you want to do is make sure that you have your log part by itself. Okay, so I'm just going to say isolate log, right? So this whole thing, right? Log base 2 of something. And that one is already isolated, okay? I'll say log part because I don't want people to think that you can just isolate the log. That's like, and I just see people trying to do that, but that's like trying to isolate a plus sign. Right? That doesn't make any sense. But we're trying to get the log part by itself so that we can figure out what x is, okay? Then once you get that log part by itself, now you can change it to exponential form. So you're going to do the base of 2 raised to this power equals this number, right? So change to exponential form. Okay. Let's do that here. So 2 to the x power equals 64. Okay, then from here we want to see, can we make those bases the same like we did yesterday? Remember when we started off and we had the equation kind of started here and it asked us to solve for x. Well, really from here it's just going to become the same as what we did last time. So if we can change this 64 to be 2 to the something power. And so if we can get those bases to be the same, that's going to be the easiest way to go about solving these, right? Because if I, put my calculator 2 times 2 times 2 times 2 times 2 times 2, you'll see that I get 64 there, right? And since my bases are the same, they're both 2's, now I can set my exponents equal to each other. So it's kind of like the bases just go away, right? And I'm just going to put these guys equal to each other. So then I just get my answer is x equals 6. Right? So the log base 2 of 64 is 6. right? Because remember what you're trying to solve for here when you're saying, you know, what is this log? You're trying to figure out what is the exponent on that base. Okay. All right, so I guess one other thing here, and then solve for x. Okay. All right, let's look at another one here. That was, oopsie. Okay, so let's solve this time for log base 125 of 5 equals x. Okay, so I want you guys to try and follow those 3 steps, right, that I said above here. And let's see what you can come up with. You can figure out what x is in this case. Okay, this one gets a little bit tricky here, so let's look at it. See if you started off the right way, though. Right, the log part is already by itself, so that means we're going to change it to exponential form. So 125 raised to the x power equals 5. That's what you should have for your next step there. All right, but now we need to get these bases to be the same. Right, and so remember that, you know, the exponent on my 5 here is just a 1. It's kind of like a little invisible 1 here. And then I can change this, right? So if I'm thinking about, and since this is already my base of 5, that's what I'm trying to think is, you know, 5 to the something power 125, and it is 5 to the 3rd power is 125, and then I still need to keep that x out there, right? So I really have 5 to the 3x power equals 5 to the 1st power. Right? And now my bases are the same, so I can set my exponents equal to each other. So I get 3x equals 1, and then I'll just divide by 3. So x equals 1/3. And 1/3 would be your answer on that one. Right? Okay, any questions on that? Let me see if I put this 1/3 back in here. Let me go back to this point here. So if I said, okay, I'm going to put 1/3 just to check it, right? Back in place in here. I mean, you're not going to want to put it in here because that's going to, you know, you're not really sure how to check that, but you could put it in here. And we're thinking 125 to the 1/3 power, right? And that does give us 5. But another thing that you could do, which might be easier, I would say for most people, is just to put that 1/3 in here and maybe see it. Right, might be able to see it a little bit better. 5 times 3 times 1/3, right, equals 5 to the 1st. So 3/1 times 1/3 is just 1. So 5 to the 1st equals 5 to the 1st. Right, so this does check out in there. Whenever there's a way to, you know, solve something, you can always check it. Let's take a look for those checks. Hey, questions on those first 2 examples that I can help with? Everybody seeing where we're putting the numbers, why we're putting the numbers where we are? Okay, let's do example 3. Okay, so this time I want you to solve log base 3 of 1 over 27. So we got a fraction this time. So log base 3 of 1 over 27 equals x. All right, so again, we're going to change it to that exponent form. 3 to the x power equals 1 over 27. All right, so this one looks kind of weird because we've got a whole number here, but then on the other side we have a fraction, right? But notice if we're so kind of ignore the 1 on the top for a minute. We're going to come back to that in just a second, but focus on your base here. So I've got a base of 3, and I'm trying to think, is there a way I could change this 27 to also have a base of 3? How could I do that? Can somebody tell me?
Would it be 3 to the 3rd power?
Yeah. So I want you to change that 1 over 27 to 1 over 3 to the 3rd power. Right? 3 times 3 times 3 gives us 27. And we're just rewriting it because we need these bases to be the same. Okay, but now we've got to do something else here because our bases, like we got 1 over, and we can't be dealing with that 1 over. So we've got to move that 3 to the 3rd power upstairs. And remember, when I do that, that makes that exponent negative. Remember how when we did the properties of exponents, and if somebody was downstairs, we flipped them upstairs, right, it changed the sign. And so that's what's going to happen here. So I've got 3 to the x power equals 3 to the negative 3rd power, right? And so now that my bases are the same, I can just put my exponents equal to each other. So x equals negative 3. Okay? And I expect my answer to be a negative number here because this is a fraction. Okay? So whenever the inside stuff here is a fraction, my exponent is always going to be negative. Okay. What questions do you have on that one? You guys feeling okay with these logarithms so far? I know sometimes it's just like, if it's the first time you've seen them or if it's been a long time since you've seen them, it really, can be, difficult to wrap your head around. You got to ask questions and make sure that you're really, really thinking about, okay, what is she doing? Why is she doing that? Right? Remember, you always want to ask yourself these, not just how am I doing, but why and what if. Right? Those are always good questions to ask yourself on these. Okay, let's look at another one here. So let's go over here for example 4. So I have you solve log base 2 of, so in parentheses, 3x plus 5. I'm doing log base 2 of all of that equals 4. Okay. And even though this looks a little bit different, we've got some x's and we've got an add sign in there, we're still going to start it off the same way. Change it to exponential form. So 2 to this power equals all of this stuff inside, right? All of that. So we've got 2 to the 4th power equals 3x plus 5. And now I just want to simplify this. Well, I know 2 to the 4th power is 2 times 2 times 2 times 2, which is 16, equals 3x plus 5. And now this is just an equation that you've solved a lot of times before. Just to get x by itself, let's subtract the 5 over, and then we'll divide by 3. So x equals 11/3. Okay. Like I said, I haven't seen the final exam yet, but in years past, this tends to be one, that I would definitely focus on. Make sure you know how to solve these log equations. And sometimes they put, more stuff in it. Not just as easy as maybe the first 3 were, but maybe some like these next few are going to be. Okay. Questions on that one? Okay, example 5. Woo. Right, so again, we're solving. This time we have 1 plus 2 times log base 3 of x minus 5 equals 7. Okay, so we're finally getting into the parts where log is not by itself. Remember I said the very first step that you want to look for is to isolate that log part. All right, and what I mean by log part, I'm going to just underline it here. All right, so from here over to here, all right, we want to isolate that part. So we need to get rid of these other things that are over here. All right, so just like with any other operation, if you were going to try and, solve, 3x plus 5 equals 7, right? You're going to do your addition or subtraction first, right? And then do your multiplication or division. Same thing happens on this, so don't think anything is different, right? So we're going to start by moving that 1 over, right? To undo that adding 1, we're going to subtract the 1 over. So then that will give me 2 times log base 3 of x minus 5 equals 6. But then see, that log part is still not by itself because it has that 2 times out in front. So I want to divide both sides by 2 now. All right, so that way those 2's will divide out, and I'll be left with log base 3 of x minus 5 equals 3. All right, so now we're finally to the point where we were above, right? The log part is by itself, right? And so I want you to try and take it from here and solve it the rest of the way down, okay? Because from here down, it's the same as what we were doing. So let me see what you guys can do with that. Give you a couple of minutes, and then when you get your answer, write it into chat. Don't hit submit yet. Remember, you can always send it to me privately. You don't have to send it to everybody. You can send it to just the host. So if you feel better about doing that, then do that, okay? Let me give you a few minutes. I want everybody to make sure you have put your answer in the chat box. Okay, 3, 2, 1, hit enter. See what you came up with. Awesome. Those of you that answered there are doing really good. Remember, if I'm asking you to do this, I want everybody to participate in that, but you can send it to me privately too, okay? And that's just fine. But let's see how they came up with that. Right? 'Cause I'm not sure if everybody got that. So if we have 3 to the third power equals x minus 5. So 3 to the third equals x minus 5. 3 to the third is 27 equals x minus 5. So we need to add the 5 over, which gives us 32. Okay. So that's all there was to that one. Okay, so I want you to try this next one. Try not to look back at the last one if you can, but if you get stuck, then look back, right? But remember on your homework, if you have to keep looking back at your notes to know how to do it, then you don't know it well enough for the test, right? And know it well enough for your next class. So please make sure, just like be honest with yourself, right? Do I need more practice on this? Then work more similar questions like it, okay? All right, so everybody try this one from start to finish this time. So -2 plus 3 times log base 2 of 2x minus 7 equals 10. Okay, so follow those steps for solving logs. Let's see what you come up with. So remember again on this, I want you to type it in your chat box when you get done, but don't press enter quite yet. If you want to send it to me privately, just click on that down arrow where it says everyone and just click on host instead. Hey AJ. AJ, will you grab me some ice water? Here's my cup. Here's my cup, bud. Here, I got a cup right here. Thank you so much. Let me see by raise of hands if you're stuck anywhere. Just raise your hand on there. If you're stuck and not sure what to do next. Thanks so much. You should enter your answer into the chat. You should end up with a fraction on this, so if you do, right, that's fine. Okay, go ahead and press enter if you haven't yet. You come up with there. Yeah. Okay, good. And some of you wrote it as a decimal, and that's perfectly fine, right? Either one is great. Okay, let's make sure everybody knows how to get there. All right, so I'm going to start off. Need to get rid of this subtracting 2, so I'm going to add 2 over. That's going to give me 3 log base 2 of 2x minus 7 equals 12. All right, then I need to divide both sides by 3, because again, I'm trying to get that log part by itself. All right, it's not by itself yet. So I've got log base 2 of 2x minus 7 equals 4. All right, now I need to change it to an exponential. So I'm doing 2 to the 4th power equals all of that. All right, so 2 to the 4th power equals 2x minus 7. Well, 2 to the 4th power is 16. And then again, I'm just trying to get x by itself now, right? So I'm going to add the 7 over. So I have 23 equals 2x, and then I just need to divide by 2. And so you could have left your answer as 23 halves, or that divides out to be 11.5. Either one is great. Okay, it looks like a lot of you got that, so that's awesome. Okay, I want you to, be confident with what you can do. Sometimes it gets like a little bit like, I don't know if I'm doing this right or not. Okay, but that's awesome. You were able to get there. Okay, let's look at the next couple that we're going to look at are a little bit different. Okay, so before we do them, I want to talk about what happens if we have like log in more than one part of the equation. So far we've only seen like log base 2 of something in one part of the equation. But what happens if I have a log in more than one place? So let me give you an example, but leave some space here. I'm going to write a few things here above that. So if I go, let's see, example 7. So I'll look at ones that look like this. So if I have log base 2 of 3x minus 1 equals log base 2 of 5x minus 7. Okay, so when we have a log in more than one place here, okay, you want to make sure you have one log on each side of the equations. Okay, so let's see, I want to say if equation, ooh, that looks funky. Equation has more than one log, get a log on each side. So meaning this could have started off with both of those logs on one side of the equation. We want to move it so that there's one log on each side of the equation. Okay, and notice that these bases have to be the same. Okay, they have to be. If you had log base 2 of something equals log base 3 of something, you'd be stuck and you wouldn't be able to do anything from there. Okay, so we want to make sure that these both have, and they always will have, the same log right now when you are dealing with those different bases of logs. Okay, they'll talk about that more in your next math classes and stuff, what happens there. Okay, but then you can set they call it the argument. I don't really like that, but I'm just going to kind of underline them, right? So you can set it, those parts equal to each other. So as long as they have the same log, right, you can set the arguments equal to each other. So that means basically kind of that log base 2 on both of those kind of drop off, and we're just left with 3x minus 1 equals 5x minus 7. We don't even have to worry about those log base 2. Okay, so let's say we're the same. And then we'll just solve it like we have. All right, let's subtract that 5 over. Add the 1 over. And then I'll divide by negative 2. So I get x equals 3 on this. All right. And again, you can, try and check these as well, right? If I put 3 in place of x up here, right? 3 times 3 is 9, minus 1 is 8, right? And then if I do that over here, 3 times 5 is 15, minus 7 is also 8. All right, so you get the same thing on both sides. We can tell that checks out, and that is our answer. All right, so if there's more than one log, just get one on each side, and then they have to be the same base, and then you can just set those other parts equal to each other. Okay. So it's just more of remembering. It's actually probably the easiest ones to solve with these logs, but it's just remembering that that's a property that you can do on this. Okay, all right, let's try another one. Example 8. Let's solve log base 5 of 9x equals log base 5 of 3x plus 8. Okay, so go ahead and solve that one. Okay, when you get done, look up at the screen and see if that's what you came up with. All right, hopefully that's what you guys were able to come up with on your own there. But what questions can I answer? That's pretty much it on 6.7. So are there any things from any of those examples that you want more clarification on that I can help you with? Okay.
I don't know about everyone else, but I feel like I get it pretty well.
Okay, good. See, that's good for me to know. Like, are you feeling good about it? I was just going to ask everybody to maybe write in their chat, like on a scale from, 1 to 10, 1 being, I don't know what you're talking about, Becky, to 10 being, I feel like I get this really, really well. Okay, so again, I want you to put it in your chat box. Again, you can just send it to me privately if you want to. Just send it to the host. If you don't want everybody to know, it'll just kind of help me to know where everybody's at. Okay, so go ahead and just put a number in from 1 to 10 so I can just tell how you guys are feeling on this. Need to hear from more people. Aw, thanks, Elizabeth.
Becky, will you be teaching 1010?
Yeah, I am. I'm teaching 1010 in the summer, and I'm also teaching a 1010 in the fall. So I think I just have one section both semesters.
Wait, did you say?
Say that again?
Okay.
In the summer and in the fall. Yeah, I'll have one section. So I haven't looked to see if my section in the summer is full yet. I know it was getting full. All right. Somebody wanted to maybe just look back here at the first couple of examples, and I'm not sure exactly, what part, but I'm thinking maybe this, maybe this 2 to the 6th power, because most of this is the same, what we're doing down lower, but sometimes it's hard for people to figure out, how to come up with those numbers, and so remember that you're trying to make that base the same. And so one way that you can kind of look at this, right, is you're trying to figure out 2 to the what power equals 64. And if you don't know what that is right off, and that's fine if you don't, you just need to use your calculator to just kind of help you, right? So you're going to say, okay, well, what's 2 to the 4th power, right? So you try that and you're like, oh, 16. Okay, well, let me go more. 2 to the 5th power is 32. Not that one, right? 2 to the 6th power. And so I can see, oh yeah, it's 2 to the 6th power. So that's how I'm getting that, 2 to the 6th power. Because I think oftentimes it's going from here to here where a lot of people have their question. Not quite sure what you're doing, but you're just thinking 2 to the what power is going to give me 64. Right? Or on this other one, like on example 2, right, we were thinking 125's got to be 5 to the what power equals 125. Right? And so just using your calculator, raise it to that power. Right? Does everybody know where the power button is to raise to the power on your calculator? Okay. Because that's, you gotta, most of the stuff in Module 6, like, you'll miss on the final exam if you don't know how to use your calculator correctly. So, if you're just kind of struggling on some things and it's calculator related, like, that's still a very valid part of asking questions about, right? Because you're going to need it so much on this last module. Okay? So if those come up for you, don't be afraid to ask. There's a lot of people in this class with the same calculator too, and so helping somebody else out by asking those questions. All right, guess what, guys? We are on 6.8, and this is the last module of the semester, right? New material. Can I get a hallelujah? Woo, woo, woo! Right? Can you believe it? We are there. We are on the last one. Okay. So, of course, we got to talk about applications using log functions. Okay, there are real things that we use these logarithmic functions for. Right? It's not just some kind of crazy math thing that you won't, that you wouldn't use anywhere else. Maybe some of you are like, I will never use it in my job, and that's valid. But there are places where this can be used, okay? So one of the things that we're going to talk about is the Richter Scale. Does anybody know what the Richter Scale is? Probably should have heard about it in the last month or so.
Isn't it like an earthquake meter thing?
It is, exactly, an earthquake meter, right? And so it's just what they use to be able to figure out some things about earthquakes. So it's kind of funny that it's, well, not funny, haha, but interesting, I guess, or we're talking about the Richter scale here, right? And those of you that live, out, more west in Salt Lake have probably been feeling a lot of these earthquakes. I've only felt one up here in Heber, and that was the very first one. Other than that, I haven't felt any of the aftershocks, but it's been kind of crazy, right? But so the Richter scale, it measures the magnitude of an earthquake. So let me write this down. So this M of X is going to be something that we're talking about here, and that's the magnitude. Okay, so the magnitude of an earthquake, it compares the amplitude of the seismic wave. So remember, that's like, you know, how much, and I don't know if some of you have felt this. Some people have told me that, you know, some of my family that lives in Salt Lake and, you know, other students and stuff have said, when I, you know, feel these earthquakes or these aftershocks, I actually like can kind of see a little bit of, you know, like this weird wave kind of thing happening. Okay, and that's what's kind of happening with it. So you've got this, you know, seismic waves, you know, during the earthquake, and so let me write down the rest of this so we can talk about this. So the magnitude is going to be found by taking the log of x over this 0.001. Okay, and x, let's see, okay, and x in here is the seismograph reading in millimeters. So have you guys ever seen what, like when they're looking at the earthquake, a seismograph has these little, you know, things showing, you know, it's kind of like, you know, kind of going up and down and stuff like that. And so when you see a big spike on it, that means that there was an earthquake there. And so they're talking about like the millimeters, how long those millimeters are, right? That's what they're kind of looking at to compare here, right? So this is the millimeters on the seismograph. Did I spell it right? That looks weird. Seismograph. I think it's right. Okay, so how long those little things are there. All right, and so that's kind of, you know, one of the things that we're going to be looking at. This is just one of the applications that we could be, you know, dealing with. So let's look at just our example here. I'm trying to keep that where we can see this. Okay. And so for example 1, all right, so part A, I want you to use, oh my goodness, use the formula, right, above here, to show that a magnitude, right, of 0.001 equals 0, right? So we're talking about this, right? So if our magnitude, so remember that's in millimeters, so if we have, you know, the millimeters on the seismograph, this is really teeny, right? So, but, you know, but they have special instrumentation that can kind of tell what those, you know, are. Back in the olden days, they had to kind of, you know, it was not as precise as they've been able to get it now with computers and everything, right? But so this is just saying, this is what X is. It's saying, okay, if the magnitude is 0.001, right, or, yeah, so if we're trying to figure out the seismograph. So if the magnitude of this, right, so we're going to put that 0.001 in place there. Okay, well, what is anything divided by itself? 0.001 divided by 0.001 is just going to be 1, right? Anything divided by itself is 1. And so if you put in your calculator the log of 1, what do you come out with?
Is it just 0?
It is 0. All right, that's what you should get on your calculator when you put it in. Because think about what we're saying here, right? I'm going to kind of write this equals y in here. I want to talk about this, right? And it has this missing base 10. Remember we talked about common logs, and if it doesn't show the base there, it's meaning base 10. So it's saying 10 to the what power equals 1, right? 10 to the what power equals 1. Well, anything raised to a 0 power, right, is 1. And so that's why the log of 1 is 0, because we're trying to figure out what is that exponent there. Okay, so that's the first thing you got to see, is that, you know, that if our seismic reading, right, is 0.001, right, then that means the magnitude is 0. There's nothing showing as far as any kind of earthquakes going on. Okay? But part B, what about if I asked you to find the magnitude of 80,000? Right? So magnitude of 80,000. Right? So this is kind of crazy. Well, we're going to put that 80,000 in place of x, right? So we'll have log of 80,000 divided by 0.001. Right, so let's go ahead and divide those out inside there, right? What's 80,000 divided by 0.001? Right? What did you guys get? You should get a pretty big number, right? When we're dividing by a really small number, that makes that top number even bigger. Anybody do that? You don't have to do the log part yet. Just divide what's 80,000 divided by 0.001. Should get 80 million. Right? And then if you put in your calculator, what is the log of 80 million? Right? Then we're going to approximate that just to 1 decimal place. Okay? So we're going to round all of our answers on the Richter scale to 1 decimal place. Okay? So it should be about 7.9. Is that what you guys came up with? Right, so just in your calculator, right, you did the log of 80 million. Should get like 7.903, blah, 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 blah. Right, we're just going to say it's about 7.9. Right, so this is when people are saying, you know, what's that?
Oh, sorry.
No, you're good. Did you have a question? Okay, I don't hear you, Elizabeth.
Oh, sorry, my computer's being all weird, so
That's
like
okay.
I'll talk and then it'll like glitch out and then. So with the answer 7.9, would that be like the magnitude of the earthquake? Like it's a 7.9 earthquake?
Yeah, exactly.
Is that saying?
Yeah, that's exactly what it's saying. So is that a very big earthquake?
Oh, okay, cool. I was just wondering.
Yeah. So that's a huge earthquake, right? That'd be crazy big. Like, what's the biggest one that we've had? I can't remember. It was in the 4s. Is that 4.5 or 4.6? Does anybody remember? It's the biggest one we've had the last month or so. Nobody remembers?
I thought it was a 5.7.
I don't think we had anything in the 5s, did we? Maybe we did. I know over 6 is where like a lot of damage happens, and when you're in the 7s, lots of damage happens. And then this one, like the 7.9, it's almost to an 8. That is like when you see like buildings being, you know, basically leveled, and so 7.9 is a huge earthquake. Has anybody been in an earthquake that big before? Or okay, so Megan thought that the big one was like 5.6.
So on the equation, it's x over 0, 0, 1. Is that assuming that like the Earth kind of like shifts a little bit, and if it's like, oh, does that make sense?
Yeah. So the Earth is going to shift like a little bit all the time, but we never feel it, right? So they're just saying if it shifts, you know, more than this amount, you know, then we're going to count it as like an actual earthquake, right? But yeah, because the Earth is constantly, like all the, you know, the plates and stuff underneath us are constantly moving. But sometimes they're moving so little that it doesn't, you know, we can't feel it on the, you know, top of the surface. So yeah, so that's kind of what that's accounting for. Good question.
That's kind of cool. I didn't think like, you know, the base of our Earth would move at all. And I think that's interesting.
Yeah. I know. No, the stuff all, you know, underneath, like a lot of it's kind of like on top of like magma and stuff like that. I know in those, you know, instances, it's kind of like floating there. But that's kind of what's happening with those plate tectonics, right, when those are moving. But yeah, we have so many all the time that we don't even feel, right? Because it's hardly, you know, moving at all. It doesn't make any difference on the surface of the Earth that some of those are underneath, okay? All right, let me see. I wanted to do, so the next one, so part C, all right, I want you to figure out, so show that an earthquake, help me, okay, earthquake, at a 6.7 on the Richter scale. Right. Had a seismograph reading 10 times larger than one that measures 5.7. So what I'm saying here is, okay, so when we're looking at the difference between a 6.7 on the Richter scale and a 5.7, right? A lot of people look at that and go, oh, it's only 1 point difference, so it couldn't make that much of a difference, right? But what I want you to look at now is it's that 1 point that's happening there, right, actually means that it's 10 times larger, right? So that's quite a bit. And if it was a 4.7 compared to a 6.7, that would be 100 times larger, right? So as it goes up by 1 point, it's, you know, increasing by 10 times each of those times, okay? So let me show you what I mean here, right, to help you see that. So if we have the, let me write this here again. Right, so here's our thing for the Richter scale, right? So this time we're given that magnitude, right? So I want to compare the magnitude of a 6.7 and a 5.7. Okay, so if we do the 6.7 one here, so 6.7 equals log of x over 1.007, and I want to compare that to a 5.7 equals log of x over 0.001. Okay, and so if I'm trying to find my x on this, right, remember that I want to change this to exponential form. That's what's going to be easiest for me, to be able to solve for that x there, right? It's kind of hard because it's stuck in that log. But I can undo that. Remember, this is in base 10, right? That common log, if it's not shown, is in base 10, and so is this one. All right, those are both in base 10. So if I was to rewrite these in exponential form, I'd have 10 to this power equals this, right? So just like we did in the last section, right, where we were solving these logs, now we're just putting some, meaning behind it, like comparing, right, these, numbers on a Richter scale, how those would compare to each other, right? So then if I rewrite this, I've got 10 to the 6.7 power equals x over 0.001. All right, now 10 to the 6.0 power is going to be, or 6.7 power is going to be a pretty big number, right? But go ahead and kind of put that in your calculator so you can figure out what's 10 to the 6.7 power. Okay, so I get this number that's like 5011872, right? And maybe I'll just do to 0.3. It keeps going more than that, but let's just go out to at least there, right? And that equals x over 0.001, right? But now, right, I need to solve for x, and right now it's being divided by 0.01. So I need to times both sides by that 0.001, right? Because that's going to get rid of these on this side. But if I multiply that side by 0.01, then I need to multiply this one by 0.001. Okay, so now take that big long number and multiply it by 0.001. And so you'll notice that all it's doing is moving that decimal point, right? Because when we're multiplying by powers of 10, that's all that's happening. And when we're, multiplying by, this is a really small number, right? Then it's going to make our answer smaller there. So we've got, it should be close to, let's see, 5,011. Maybe I'll write it as 0.87 or something like that. Okay, this is what x equals. Okay, so now I want you to do the one for 5.7, right? So figure out, solve this for x, right? If we have a 5.7 magnitude earthquake, right? Figure out what the x would be on this. Let me give you a couple minutes to try that. Okay, so when you solve this, right, you should have come up with this time the 501.1, I guess we could say 9 if we round that to the nearest hundredth there, right? But it was really like 8.7, because really all that was happening here was we were just moving that decimal point, right? And so I just want you to see that, you know, if x is 501 and x is 5011, right, you can see that this 5011 is 10 times bigger, because if I multiplied the 501 by 10, I'd get the 5011 there. And so, so it's just kind of, I mean, cool to understand a little bit about the Richter scale and, you know, what those numbers mean on the Richter scale, because a lot of times people are just kind of like, I don't know, you know, it was a, what did you say, a 5.6. Well, what does that really mean, right? But that is the magnitude of, you know, of what was happening with the earthquake. Right? All right, I think let's take a little break right there. We've been going for an hour, and so let's take a little break, and then we'll come back when we have some more types of applications that I want to talk to you about. Okay. Is anybody else having connection problems? Elizabeth was asking. Is everybody able to hear me okay, too? Am I breaking up at all? Okay. Elizabeth, you could switch to your phone if you have the WebEx app on your phone. That sometimes helps some people.
Screen will freeze, and then like 2 minutes will go by, and then everything will like pop up again, and it'll like go so fast.
And you're like, wait a minute, what? Remember, I am recording it though too, so you can kind of go back and look at some of those parts if you need to. But yeah, if you have a phone that has the app on it, you could. I know some people that have problems with their laptops have had more success with the app on their phone, but you'd have to just go and download that app, though. It's a free app, but you'd have to go download it.
Yeah, I'll have to log on my phone right now. I have the app, so.
Okay, yeah, why don't you try that and see if that helps.
the
Okay, let's get started back in here again. So for this next part, we're going to be talking about population growth. And I talked about before how population growth, oops, let's see, am I muted? Hold on a second. There we go. Now you should be able to hear me. Okay, so the next part that we're going to be talking about is population growth. And so we've talked about how things grow exponentially, and population is definitely one of those things that has this exponential growth to it, right? So it's usually a percent growth is what we're talking about. And so like, you know, bacteria grows that way. Even things that we've had going on with the corona stuff right now, like the amount of number of cases that there are per day, have been growing at an exponential rate, and they're hoping at some point that's going to level off, right? And then start its way back down. And so that's kind of what we're talking about here. So, but we're going to talk about just population of the world, first of all, for this example. All right, so the world population, let's write down this. Was 4.8 billion in 1985. All right, so it was a while back, but it was 4.5 billion there. Okay, with an estimated growth rate of 1.8%. Okay, per year. So every year it was going up almost 2%. Okay, but not quite. So if we assume that it's going to keep following that pattern, right, then we want to find the population in, let's just do this year, 2020, right? We have a census this year, so be able to, figure out what that population is of the United States, but this is going to be for the world, but we can still look that up and see how close it is to, if this growth rate was continuing at that same path, right? That way. And then let's make sure that we will round our answer to 2 decimal places. All right, but let's talk about this formula that I have up here, because you got to understand the formula, first of all. You don't have to have it memorized, right, since you're going to be able to use your notes on the final exam, but it'd be good to make sure that you know what each of these things stand for. Okay, so this P of 0 represents the initial population. Right, so it's kind of like your start, right, your start amount. All right, and we're starting in 1985, right, with that 4.8 billion. Okay, now this R up here, right, is your growth rate, and then T is the time in years. Right. And then that, P of T is how much you're going, like the population at the time you want to know. So like this one, right, is going to be the population in 2020. Okay, so you can kind of think about it as your end amount, or, the population at a given time is really what that P of T means, right? So population at a given time. All right, that's what we're talking about here. Okay. All right, so those are just the different parts of it. And E, some people are like, well, why didn't you talk about E? All right, remember, E is not a variable. E is a constant term. Remember, if you put E in your calculator, it's like 2.718, blah, 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 blah. Right, and so we say it's approximately 2.72. But I'll write that over here again to remind you that E is approximately 2.72. We're not going to be using 2.72. We're going to actually use the E button on your calculator, right? But just to help remind you that that's not a variable, we know what that is, okay? So let's put in what we know here. Let's see what we can figure out, what what they estimated that the population would be this year if it continued at that growth rate. So we're going to kind of compare that and see if this actually was. All right, so we've got this 4.8 billion, right? And so we're just going to use, you don't need to put like the billion part on, we're just going to use that 4.8. We're going to know that our answer is going to be in billions, right? So let's go ahead and put these things in then that we know. So P of t is what we're trying to find, right? This end amount. And so we know that that initial population is going to be 4.8. Right? And then E, so I'm going to times that by E, to the growth rate. Well, remember that our, I'll change this here, 1.8%, we've got to change that to a decimal, so it's going to move back 2 places, right? So that's really going to be the same thing as 0.018. Okay? And so we're going to put that in place of our R. And then in place of t, right, we need to put our time. Well, that is the number of years, right, that we've had. So we're going to be figuring out, we got to kind of do over here. I'll just write it. Oops, I need to do a different color there. All right, so when we're talking about the time, right, we're doing the 2020 minus the 1985, right? That's what we were, that was our start year, and this is our ending year. Okay, so that's going to be 35 years is what we're talking about. We're trying to see how much, right, what is our population going to be 35 years later. So this is going to be to the 30 times 35 up there. Okay. Is everybody okay with what I put in there and why I put that in there? Speak up if you're like, I'm not quite sure. Okay, so now a lot of this is just going to be using your calculator, right, to figure it out. So with this one, right, it'd probably be best if your calculator can't put all of this in at the same time, it'd be best for you to figure out what, 0.018 is times 35. Okay, which is 0.63. So I'm just going to write this down here. So we've got 4.8 times e to the 0.63 power. Right? So again, if your calculator won't do it all at the same time, and some won't, right? So you follow these steps I'm showing you here. If you tried putting it in and then you don't get the same answer I get here in the end, right? So now we have to do the e to that power, right? So I'm going to be doing this part right here. So in your calculator, put e to the 0.63 power. Right, so I get this number that's a long decimal, and I want to keep that long decimal in your answer. Don't try and like cut it off, right? Like with what the digits are that you see there, because it keeps going and going and going, and that's going to make a difference in your answer. So then you'll do 4.8 times, right? I'm not going to write all of these numbers down in here, but blah, 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 right? So you've got to keep that whole thing in and then press times by 4.8. Right? So you should get, right, that P of t is, if we round to 2 decimal places, like it says there, 9.01. Right? And remember that this is in billions. Right? So 9.01 billion is what they estimated the population is. Okay? So I want to go and just kind of see here. Move this over, oh goodness. I am just going to do a little Google search here. All right, let's look at what is the population of the world, oops, 2020. Oh, so it's closer to 8 billion, it looks like. All right, so that means that it wasn't going up at the same rate all of those years, right? At some point, it must have slowed down a little bit. So yeah, so the population is closer to 8 billion, right? Let's see. What? Oh no, that was a projection. Let's see. What does this one say? Oh, these are just by each country, but let's look at it here. Wow, that's pretty crazy. Yeah, so it actually isn't quite 8 billion, right? And it's closer to 7.7 billion, right? So it's definitely has decreased and went down, you know, somewhat. And, you know, there can be a lot of reasons for that. Maybe some people just aren't having as many kids. They had that thing in China also where they could only have one child, right? And I think that maybe even started in around 1985. And it was just recently lifted, and I think they can now have 2. But that could have drastically reduced, you know, the population and stuff from what was happening before. So it's kind of cool to see, like, you know, I mean, these are, you know, projected models and stuff like that, but that doesn't mean that they're absolute. And sometimes they're closer to the, you know, correct answer than, you know, than not. But this one wasn't as close as I would expect it to be. Okay. That's kind of cool to see, you know, these kind of things actually happening in real life there, right? What we're going to be using this for. All right. Questions about that one? I don't see anybody asking any questions there. Okay, so we will go on to the next one. Let's see if there was.
Is this kind of like a statistics problem? Like, in order to stay accurate, there has to be like an updated version of it, like every year, every so often, or it's just not accurate anymore.
Yeah, I think that it's just hard. Like, I mean, 35 years is a long time for like a growth rate to stay the same, you know, and there's a lot of things that could affect that growth rate. So I think if we, you know, if you would have looked at it maybe 10 years later or something and then readjusted, look at those 10 past years and said, okay, well, what was the change in that growth rate? And then try and go from there. That could definitely, you know, help out and stuff. So yeah, I mean, that just goes to show you that growth rates are not, you know, like a consistent thing all the time. But it is pretty cool to see, you know, people, they use this kind of population growth stuff with wild animals and stuff too. So, you know, I mean, you know, in Utah and a lot of the states out west, there's a lot of, you know, hunting that goes on. And so they try and figure out, you know, what the population growth would be on these different animals. And that's kind of how they figure out how many hunting tags that they'll, you know, that they're going to allow, so that the population doesn't get too decimated, right? They really have to look at all this stuff to make sure. And yeah, and they have to keep analyzing it, you know, every couple of years because things can change, definitely. Yeah, that's kind of cool to see how that happens here. All right, let's see here. All right, well, let's look at the last type of thing that we're going to be talking about today. Has to do with radioactive decay. So there are some elements, right, that are, so all of the elements kind of have, they decay at different rates. So like, you maybe heard of carbon-14 dating, and that's just, that helps scientists figure out like how long, you know, they use it a lot with people, like, so I know sometimes this is like some people like, oh, I don't know, that sounds gross, but, you know, like if somebody died and they don't know how long ago they died, they can use carbon-14 dating to figure that out. And so like even, you know, when they're trying to figure out, you know, how old were some of those mummies, you know, that were in, you know, some of the pyramids in Egypt and stuff, they can use carbon-14 dating to figure out how old they were, because as you know, when someone dies, the amount of carbon in your body decays by a certain amount, and it's pretty constant. You know, that's one of the things that's not going to really change, like population. A lot of things could affect that. Okay, the only thing that could really affect, like, you know, how your body is maybe decaying, you know, would be like the temperature and stuff like that. Those kind of things could affect it too. So there are, you know, some things that are, you know, you can tell from this, but I think it's kind of cool to see what happens. But maybe you've heard of something called, of half-life. You guys heard of that before? And you'll hear, if you haven't taken chemistry, but you need to take chemistry still, you'll hear that a lot. So, but we're going to talk about specifically radioactive elements. Okay, and talk about this radioactive decay. Okay. And so basically, there are radioactive elements, you know, that are unstable, and they're going to change over time. And so we hear this word half-life that is kind of talking about that amount of decay, right? So let's just put down, it's the time it takes for half the substance to decay. Right? So half the time is what we're talking about with this half-life. Right? And so there is a little formula that you'll see that kind of talks about radioactive decay and its half-life. And it's going to say this. So 1/2 times A equals A times, and then parentheses, e to the r times t power. Right? And so, and again, remember, if we're thinking about, you know, these different parts and stuff, A is the amount, like the start amount of that radioactive. A second, so this R represents, right, the decay rate. Right? And different elements have different decay rates, right? Even, you know, radioactive elements. Okay? And T is our time in years. Okay? And then and yeah, so sometime, and the E again is just that part that we were talked about, is that just that regular E, but this A in both of these places is kind of like our start amount. All right, so the amount, how do I want to say that? I'm just going to write it as start amount. I'm trying to find a better way to say that, but I'm not sure if I think of a better way to say that right now. So, okay, but, and it's talking about that, you know, that half-life there. Okay, so if we look at, let's look at this example. So we write down this next part. So carbon-14 right, has a half-life of 5,730 years. Right, that's a long time. Carbon-14, right, has a half-life of 5,730 years. Okay, and so we want to try and find some of the things about this carbon-14 using this formula that's given to us here. Right, so just 1 second. I keep thinking that this A is kind of throwing me off in this formula. Hold on just 1 second. Oh, it's represented by 1, meaning like 100%, because it's going to start with, you know, like, so the full amount, right, before something starts to decay, right, everything is there. And so we'll replace those with a 1 because it means like 100%. Okay, so let's go to this then and put in what we know here. Try and find this. So if we have 1/2 times that 100%, we'll just write it in as a 1, equals 1, right, times E to the, now we're trying to find this rate, right, that's what we're trying to find. So R times 5,730. Okay, and so let's simplify this up more. So I really have 1/2 on this side equals, I'm going to rewrite this as E to the 5,730 times R. And it's just easier for my brain to have the number first and the letter second. Okay. But then we're going to go back, you know, 2 sections where we talked about solving for an exponent, right? And to solve for those exponents, we're going to have to take the log of both sides of the equation. But since we're dealing with log base E, we're going to have to use the natural log on this. So I'm going to take the natural log of this side, and whatever I do to one side of the equation, I've got to do to the other side. So I'll take the natural log of the other side. And remember what that does for us is by taking the log of both sides, that exponent that's out in front, or up on top, comes out in front and is now multiplied by it. Okay, so let's see, let's write down the next line. So I've really got the log, natural log of 1/2, right, equals 5,730 times R times the natural log of E. Right, and we talked about the natural log of E a little bit last time. If you put that into your calculator, right, the natural log of E is always 1. And so really we can kind of just forget about that part. We don't need to do anything more with that, because the natural log of E is just 1. So that just all goes away, and that's just a 1 there. Okay? But then I'm trying to solve it for R, trying to get R by itself. So that means I need to divide both sides by the 5,730. And when we do that, so go ahead and put in your calculator. Again, this is kind of, a lot of it is calculator work. You're going to figure out what the log of 1/2 is, and then divide it by 5,730. So that natural log of 1/2. And on some of your calculators, you'll have to do natural log of 1/2 and then press enter. Okay? And then divide that by the 5,730. Okay, and you get a negative number. You should get a negative number because this is decaying, right? And so that's what we're dealing with here. So that means that the decay rate, right, is negative. Let's see, we've got a lot of zeros here. 0.00001, and if we keep going, right, kind of see this, but it keeps going on and on and on after that. Okay, so this is a really, really small decay rate, right? If we're thinking about how much is decaying per year, right? It doesn't seem like it's very much, right? And like I said, sometimes people use this like with artifacts and stuff like that, you know, really old things to figure out how old something is on that. Okay. Let's see here. What else did we want to be able to find? I think if there was something else here that we wanted to look at. Double check. Should we get everything on there that you guys need to know? And oftentimes a lot of students get kind of worried about these on the final exam. I'll just tell you straight up, like the only kind of thing that I've seen on the final exam is something like that we did before with the like when you have, I'm trying to say, like compound interest, something like that. Okay, but they might ask you to find the time, you know, it's going to take on compound interest or something, but usually it's just more straightforward on that. So all right, let's see. That's what the deal was. It was like, I think I'm missing some part of it here in my question. Oh yeah, okay. So let's look at this. So let's say that we're looking at a bone fragment, okay, of something. So let's write this one down. So a bone fragment contains 20% of its original carbon-14. Okay, how old is the bone? Okay, so we're still using the information that we found in this first example, right? Because we were talking about that carbon-14. This is the rate that it, you know, is decaying. So let's go back to that equation then, right, on this. And so instead of that half, right, times A, right, it contains that 20%, right? So we're going to say it's going to be 0.2, right, equals the E to that power. Let's kind of, I mean, you're going to want to make sure that you keep that whole thing in your calculator, or if you know how to use the little, like, there's little save buttons too, like where you can save something in the memory. Sometimes on this, that is really helpful, right? Because now we're trying to find the time on this, okay? So we know that 20% is what's left, right? We know that the rate at which it's decaying is this, and then we're trying to find the time, Right, so that's what we're putting in there. So again, we need to take the natural log of both sides so that we can do this. Okay, we're almost out of time here, but let's just finish this up really quick. So remember that all of this comes out in front now, right? I'm just going to cut that, okay, times t, right? And then the natural log of e, remember, is just 1. So that really just goes away. So what we're really doing is just taking their natural log of 0.2 and dividing it by this big long number that you got there before, right? We're dividing it by the rate. That's what we end up needing to do there. Okay, so go ahead and put that into your calculator. Is it 3 zeros? Oops, I forgot a 0 on that one. So that's another reason why it's just better to keep it in your calculator, right? And sometimes you can do, another way you can do it would be, if you see like there's an answer button that says A and S on your calculator, that will take the answer from the last thing that you put in there. So you can also do that. Okay, and then when you do that, you should come out with t equals 1,301. So, sorry, I meant 13,301. So that's saying that this bone that you found is that old. Okay. All right, well, we are out of time there, but if you need to, all right, you can kind of look back on these and look back at, some of the videos too on the lessons. Remember, sometimes there's like a video right next to a question that sometimes can be really helpful if you're getting stuck on how to do one of them. But please reach out to me if you have some questions or have anything else. But yeah, next week we're just going to be reviewing for the final exam. That's all that's left to do, but they're going to be really important days to make sure you come to class because you can get any questions answered that you need help with, and also, the stuff in Module 1 and Module 2 is going to be probably a little bit, hazy in your mind since it's been a long time since we've done it. So, so keep that in mind. So we'll be reviewing, I'm going to try and do Modules 1, 2, and 3 on Tuesday, and then 4, 5, and 6 on Thursday next week, right? So we'll kind of break it up and do 3 modules in each of those, okay? All right, guys, have a super duper day. Have a great weekend. Reach out to me if I can help you, okay?
Thanks, Becky. You have a good one.
All right, you too. Thank you.